current rating of a wire depends on several factors. Firstly, the conductor material influences the current rating. Copper conductors possess a higher current rating compared to aluminum conductors. Secondly, the wire size is crucial. Thicker wires exhibit a higher current rating than thinner wires. Thirdly, voltage is a factor to consider. Voltage itself does not directly affect the current rating of a wire. Fourthly, temperature plays a role. The current rating of a wire decreases as the temperature increases. Regarding 16 American wire gauge copper wire, its current rating is 8 amps, irrespective of the voltage level. The allowable ampacity for 16 American wire gauge copper wire remains consistent due to the fact that voltage does not alter the wire's inherent current carrying capacity. To ascertain the permissible current rating of a wire, consult the National Electrical Code, abbreviated as NEC. The National Electrical Code serves as a comprehensive set of standards designed to ensure the safe installation and utilization of electrical equipment. The National Electrical Code undergoes revisions and updates every 3 years, with the most recent edition being the 2020 National Electrical Code. Specifically, National Electrical Code Table 310.16 provides the allowable ampacities for copper conductors. In the case of 16 American wire gauge copper wire, the allowable ampacity is designated as 8 amps. This implies that a 16 American wire gauge copper wire can safely accommodate a current flow of up to 8 amps without exceeding its rated capacity. In summary, the factors influencing a wire's current rating are conductor material, wire size, and temperature. Voltage does not have a direct impact on ampacity. Always refer to the National Electrical Code to determine the acceptable current rating for a specific wire gauge and material. The National Electrical Code provides guidelines for safe electrical installations, including ampacity ratings for various conductor types and sizes. The current rating of a wire, often referred to as ampacity, is the maximum amount of electrical current a conductor can carry continuously without exceeding its temperature rating. This temperature rating is crucial because excessive heat can damage the insulation, potentially leading to short circuits, fires, and other hazards. Several factors influence the ampacity of a wire, including the conductor material, wire size, installation method, and ambient temperature. The conductor material is a primary determinant of ampacity. Copper and aluminum are the most common conductor materials, but copper generally has a higher ampacity than aluminum for the same wire size. This is because copper has a lower resistance, allowing it to carry more current without overheating. The wire size, typically expressed in American wire gauge, also significantly affects ampacity. Larger wires have a greater cross-sectional area, allowing them to carry more current than smaller wires. The National Electrical Code provides tables that list the ampacity of various wire sizes based on the conductor material and installation type. The installation method can also impact ampacity. Wires installed in free air, such as overhead power lines, can dissipate heat more effectively than wires installed in conduits or buried underground. As a result, wires in free air typically have a higher ampacity than those in enclosed spaces. The ambient temperature, or the temperature of the surrounding environment, can also affect ampacity. As the ambient temperature increases, the wire's ability to dissipate heat decreases, which reduces its ampacity. The National Electrical Code provides correction factors to adjust the ampacity of wires based on the ambient temperature. The National Electrical Code is a comprehensive set of standards that governs the safe installation and use of electrical systems in the United States. It is developed and maintained by the National Fire Protection Association and is updated every 3 years. The National Electrical Code provides detailed requirements for wiring methods, overcurrent protection, grounding, and other aspects of electrical installations. The National Electrical Code Table 310.16 is a crucial resource for determining the allowable ampacities for copper conductors. This table lists the ampacity of various wire sizes based on the insulation type and ambient temperature. It is essential to consult this table when selecting conductors for electrical installations to ensure that they can safely carry the anticipated current load. When determining the appropriate wire size for a particular application, it is crucial to consider all the relevant factors, including the load current, voltage drop, installation method, and ambient temperature. It is also essential to consult the National Electrical Code and any applicable local codes or regulations. Voltage drop is a reduction in voltage that occurs as electrical current flows through a conductor. Voltage drop can be caused by the resistance of the wire and the length of the circuit. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, it is essential to use the correct wire size and keep the circuit length as short as possible. Overcurrent protection is a critical safety feature in electrical systems. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current in the event of an overload or short circuit. Overcurrent protection devices protect conductors and equipment from damage caused by excessive current. The National Electrical Code provides detailed requirements for overcurrent protection, including the selection and installation of overcurrent protection devices. Grounding is another essential safety feature in electrical systems. Grounding provides a low impedance path for fault current to flow back to the source, which helps to protect people and equipment from electric shock. The National Electrical Code provides detailed requirements for grounding, including the selection and installation of grounding electrodes and grounding conductors. In summary, the ampacity of a wire is the maximum amount of electrical current it can carry safely without overheating. Several factors influence ampacity, including the conductor material, wire size, installation method, and ambient temperature. The National Electrical Code provides detailed requirements for wiring methods, overcurrent protection, and grounding to ensure the safe installation and use of electrical systems. Always consult the National Electrical Code and any applicable local codes or regulations when designing and installing electrical systems. The relationship between voltage and current in a circuit is governed by Ohm's law, which states that voltage is equal to current multiplied by resistance, or volts equals amps times ohms. While voltage does not directly affect the ampacity of a wire, it does play a role in determining the amount of power that a wire can safely transmit. Power is the rate at which electrical energy is transferred, and it is calculated by multiplying voltage by current, or power equals volts times amps. For a given wire size and ampacity, increasing the voltage will increase the amount of power that can be transmitted. This is why high voltage transmission lines are used to transmit electricity over long distances. By increasing the voltage, the current can be reduced, which minimizes losses due to resistance in the wires. However, it is essential to note that increasing the voltage also increases the risk of electric shock. High voltage systems require special safety precautions to protect people from coming into contact with energized conductors. In low voltage applications, such as those found in residential and commercial buildings, the voltage is typically limited to 120 volts or 240 volts to reduce the risk of electric shock. In these applications, the ampacity of the wire is the primary factor that determines the amount of current that can be safely carried. It is crucial to select the correct wire size for the anticipated current load to prevent overheating and potential hazards. The insulation type of a wire also affects its ampacity. Different insulation materials have different temperature ratings, which determine the maximum temperature that the wire can withstand without degrading. Wires with higher temperature ratings can carry more current than wires with lower temperature ratings. The National Electrical Code specifies the allowable ampacities for various wire sizes and insulation types based on the ambient temperature and installation method. When selecting wires for electrical installations, it is essential to consider the installation type and ensure that it is appropriate for the intended application. Wires that are exposed to high temperatures or harsh environments may require special insulation to protect them from damage. In addition to the factors discussed above, the presence of harmonics in an electrical system can also affect the ampacity of wires. Harmonics are distortions in the sinusoidal waveform of alternating current that can increase the current flowing through the wires. Harmonics can be caused by nonlinear loads, such as electronic devices and variable frequency drives. The National Electrical Code provides guidelines for directing the ampacity of wires in the presence of harmonics. It is essential to consider the potential for harmonics when designing electrical systems and to select wires that are appropriately sized to handle the harmonic currents. In summary, the ampacity of a wire is a crucial parameter that determines the maximum amount of electrical current it can carry safely without overheating. Several factors influence ampacity, including the conductor material, wire size, installation method, ambient temperature, insulation type, and the presence of harmonics. The National Electrical Code provides detailed requirements for wiring methods, overcurrent protection, and grounding to ensure the safe installation and use of electrical systems. Always consult the National Electrical Code and any applicable local codes or regulations when designing and installing electrical systems. The National Electrical Code also addresses the use of different types of conductors. The most common types are copper and aluminum, each with its own advantages and disadvantages. Copper is a better conductor of electricity than aluminum, meaning it offers less resistance to current flow. This allows copper wires to be smaller than aluminum wires for the same ampacity. However, copper is also more expensive and heavier than aluminum. Aluminum is lighter and less expensive than copper, making it a popular choice for larger conductors, such as those used in service entrances and feeders. However, aluminum is more susceptible to corrosion than copper, so it requires special connectors and installation techniques to prevent oxidation. The National Electrical Code specifies the types of connectors that are approved for use with aluminum conductors and provides guidelines for preventing corrosion. The National Electrical Code also addresses the issue of directing ampacity when multiple conductors are bundled together in a conduit or cable. When conductors are bundled together, they generate more heat than they would if they were installed separately. This heat can reduce the ampacity of the wires. The National Electrical Code provides directing factors that must be applied to the ampacity of conductors when they are bundled together. The directing factors depend on the number of conductors in a bundle and the ambient temperature. It is essential to consult the National Electrical Code when installing multiple conductors in a conduit or cable to ensure that the wires are properly sized and directed. The National Electrical Code also addresses the use of flexible cords and cables. Flexible cords and cables are used to connect portable appliances and equipment to electrical outlets. They are typically made of stranded copper conductors with a flexible insulation material. The National Electrical Code specifies the types of flexible cords and cables that are approved for various applications. It also provides guidelines for the proper use and maintenance of flexible cords and cables. Flexible cords and cables should be inspected regularly for damage and replaced if necessary. They should not be used as a substitute for permanent wire. In addition to the requirements discussed above, the National Electrical Code also includes provisions for specific types of electrical equipment and installations such as motors, transformers, generators, and hazardous locations. These provisions are designed to ensure the safe installation and use of electrical equipment in specialized applications. It is essential to consult the National Electrical Code when working with any type of electrical equipment or installation to ensure that it is installed and operated safely. In summary, the National Electrical Code is a comprehensive set of standards that governs the safe installation and use of electrical systems. It provides detailed requirements for wiring methods, overcurrent protection, grounding, conductor ampacity, and other aspects of electrical installations. It is essential to consult the National Electrical Code and any applicable local codes or regulations when designing, installing, or maintaining electrical systems. The National Electrical Code is a living document that is constantly evolving to keep pace with advances in technology and changes in industry practices. It is updated every 3 years to incorporate new information and address emerging safety concerns. It is essential to stay current with the latest edition of the National Electrical Code to ensure that electrical installations are safe and compliant. The National Electrical Code is a valuable resource for electricians, engineers, inspectors, and anyone else who is involved in the electrical industry. It provides a framework for safe and reliable electrical installations that protect people and property from electrical hazards. The information contained in the National Electrical Code is based on sound engineering principles and years of experience in the electrical industry. It is a testament to the commitment of the electrical community to safety and innovation. The use of appropriate safety equipment is paramount.